Hello, ladies and gentlemen. Today we are going to be diving a little bit more into series and parallel circuits. Yesterday we kind of introduced just the basics of it, and now we're going to be calculating a few different things with those. So today your goal is to go through this slide, either by yourself or watching this video. Complete the day number 6 exit ticket in Google Classroom, and then finish day 5 and 6 assignment. So hopefully yesterday for the assignment you just did numbers 1 through 5, and then today you would be able to finish that assignment. Just as a reminder, remember you do not have to turn in those assignments. Those are just for your help getting you to understand the material more. So first of all, just kind of as a review from yesterday, because yesterday we talked a little bit about symbols and circuit diagrams, so I just kind of wanted to go through an example of that. So draw a picture of a series circuit with 3 4-volt batteries, a 2-ohm bulb, a 2-ohm resistor, and a 3-ohm resistor. So what that's going to look like is if I have 3 batteries, I'm going to draw a battery there, and a battery there. So I'm just connecting these. So there's 3 different batteries there. And this is a series circuit. So I wouldn't normally do this, but just so you can see where the batteries are at, I'm going to put a B next to them, battery, battery, battery. And then I would put 4 volts, 4 volts, 4 volts. And then this is all in series, so it's just one path for the charge to flow. So I'm going to have a 2-ohm bulb. All right, so for a light bulb, I'm just going to use this symbol. And I know we didn't talk about that one. There's multiple ways that you can represent a light bulb, though. That's one of them that you can use. That's a 2-ohm. A resistor. That is a 2-ohm resistor. And a 3-ohm resistor. And that is it. And that's how that would look right there. Okay. So, moving on, we're going to talk about series and parallel circuits. Don't do that. Just as kind of review, and to once again, like I told you before, show you a couple different ways that you can represent symbols in a circuit diagram. So here's another few ways that you can look at, or symbols that you'll see right here. I just used the light bulb one, that circle with an X through it. Just a few other things you might see. We won't deal with fuses a whole lot, but that's what a fuse would look like. We'll use switches, batteries, light bulbs, resistors, and then obviously wires we'll use quite a bit. So moving on to series circuit, we talked about these a little bit yesterday. Here's your definition for a series circuit. Contains only one path for current to flow or for charge to flow. The current is going to be the same throughout this entire thing, right? Because there is only one path for it to flow, that current is going to be the exact same. Every single bulb is going to be is equally as bright. And then if we are to break the circuit, whether you have a switch on here, just like in your house, if you open that switch, or if you were to, if a light bulb goes out, everything in that circuit is going to shut off, right? Well, this is why in our houses we don't wire things in series, because if you had everything in series in your house and a light bulb went out, well, then your whole house would shut off. So you don't want that. So I'm going to looking at resistance in a series circuit. In order to find resistance in a series circuit, all we're doing is we're just adding all the resistors together, right? That's how we're going to find the total resistance. Sometimes this might be called, it says R total right here. I actually like to use REQ, all right, which REQ just means equivalent resistance. All right, that's all that EQ means, is equivalent. All right, so equivalent resistance, you're just taking all the resistors, adding them together. So here you'd have 3 plus 2 plus 3. So you would get an equivalent resistance of 8 ohms. And that's all you would have to do for that one. All right, moving on to, let's take a look at how we would determine the current flowing through the circuit. Well, For a lot of these problems, you're going to have to use Ohm's law. And Ohm's law, we said, is V equals IR, right? And if you want to go ahead to help yourself out, if you want to just go ahead and solve for each one of those, if that helps you, you're more than welcome to do that. So like if I wanted to solve for I, you're going to have V divided by R, solve for R, V divided by I. Just to kind of help you out, just so you can just take a quick look over there when you need to solve for something. First one, determine the current in the following circuit. Well, in order to solve for current, I need voltage and I need resistance. Well, I can add the total voltage together and I can add the total resistance together just like we did before. So my total voltage is going to be 12 plus 12. So I have a total voltage of 24 volts. And I'm going to divide that by my total resistance. So 3 plus 2 plus 3, that one we just did. So we're dividing that by 8 ohms. So I'm going to get a total current of 3 amps. All right, now the second one says determine the current in this circuit. Just be careful when you see this. These ones have, it says K and then omega, that is kiloohms. All right, so instead of being just ohms, it's kiloohms. We have to have this in ohms. In order for it to work in Ohm's law equation, it has to be in ohms. So you can't just plug in 2 for every single one of these. You would actually have to say these are going to be 2,000 ohms for each of these. So 2,000, 2,000, 2,000. So what you're actually going to have is we have 12 volts, but now we're going to divide it by not 6, but we're going to divide it by 6,000 ohms. So you are going to get an answer of 0.002. Oops, and I'm sorry, I'm running out of room there. Amps. Okay. So that's how you go about solving for total current within a series circuit. Okay, so now you should be able to solve for total voltage. You're just adding it together. Total resistance, you're adding it together. And then total current, you are going to have to divide the two. Okay, so let's go to the next one. I don't know why it keeps doing that. All right, so voltage in a series circuit. Each bulb or any kind of resistor that you have uses voltage. It uses a certain amount of voltage. So every time a device is used, right, it's using voltage. So therefore, the voltage is going to drop. We call it a voltage drop. It's going to decrease after every single device. So the voltage drop is just the difference in voltage across an electrical device, or you can think of it as the amount of voltage that is being used by that bulb or by that resistor. All right, so in a series circuit, the voltage put out must be completely used by the resistors. And once I show you how to do this, you're going to see that you're going to kind of see how this works. But we call this Kirchhoff's voltage law. All those voltages all those voltage drops add up to equal the battery's voltage. So the voltage drop of each of these resistors here, this resistor, and this resistor, once I find each of those voltage drops, you're going to see that it actually adds up to 24. Okay, so 24 volts is what we have of potential energy, of electrical potential, and 24 volts is what we are going to use when we are all said and done. All right, so let's see what that would look like then. So let's actually calculate the voltage drop. So determine the following, calculate the current throughout the entire circuit. So just like before, we can calculate the current. Remember we said current is equal to voltage divided by resistance. So our total voltage is 12 plus 12. So we have 24 volts divided by we have a grand total of 3 plus 3 plus 2, so we have 8 ohms. So we have 3 amps once again. So that is our total current. So we can say that's 3 amps. Calculate the voltage drop for each resistor now. So now I'm going to go through And since I want to find individual voltage drops on each resistor, I'm solving for voltage, still using Ohm's law. Voltage is equal to current times resistance. So I'm going to take that 3 amps because that 3 amps is running throughout this entire circuit. Okay, so 3 amps of current, that doesn't change. That current is going to be the same throughout the entire circuit because it is a series circuit. So I know there's 3 amps of current running through this resistor. I'll just call it R1. I know there's 3 amps of current running through R2, and I know there's 3 amps of current running through R3. So what I can do for every single one of these problems is I can take 3 amps and multiply it by each resistor. So I'm taking 3 amps and I'll multiply it by 3 ohms. And then I'll take 3 amps and multiply it by 2 ohms. And then since we're already solving for the first one, R1 and R3 are going to be the exact same answer. So I'm not actually going to go ahead and do that. So my voltage drop for each one of these. So the voltage drop across R1, we're doing that 3 times 3, so we end up getting 9 volts. So this resistor is using 9 volts. We have R2 is using, we'd be doing 3 times 2, so we get 6 volts. So this resistor would be using 6 volts. And lastly, this one over here, R3, would be using 9 volts. So what you can see here is, as we talked about in the last slide, we have 24 volts of electrical potential here. So we have to use all 24. And the good way to check to see if you did this right is, do my voltage drops actually add up to 24? 9 plus 9 plus 6, sorry, that got really messy there too, is going to give you 24 volts. Okay, so that's a good way to check your answers if you're ever figuring out voltage drops. Okay, so let's take a look at another problem here. Actually, what I will do is, for this one, since this is just like one that we just did, I'm actually going to leave this one here, and I will post the answers for this one onto the Google slide itself. So if you want to work through this problem on your own, go ahead and do that, and I will post the answer for this because this is exactly like one of the problems we just did. So you can kind of test yourself there. All right, moving on to parallel circuits. Parallel circuits is where we have more than one path for the current to flow through. We have branches in a parallel circuit. So a branch would be like right here. That's one branch that has a resistor on it. This is another branch. This is another branch here. Okay, if a branch is broken within that parallel circuit, the current doesn't just stop. Okay, so if I were to take like some sort of wire cutter or something like that, and I were to just cut right here, and I cut that first branch's wire, well, current is still going to flow through branch number 2 and branch number 3 here. It's just not going to flow through this first branch. Okay, so that's the advantage of a parallel circuit, is that electricity can still flow through all of the other branches. And this is exactly how we wire our houses, for the reason I was telling you earlier, is that if one bulb goes out, then not every single thing in your house is going to go out. Okay, and I'm sure many of you might have experienced frustrations with the difference in series and parallel, maybe with Christmas lights. If you buy the cheaper Christmas lights, those are going to be wired in series. So like with Christmas lights, if one bulb goes out in those ones, then they all go out, and then you have to sit there and try to figure out which one is the bulb that's broken. If you buy the more expensive Christmas lights, they're wired in parallel, and then when one goes out, the whole thing won't go out. When we're talking about current through branches in a parallel circuit, the current through every branch is going to be different. Okay, so depending on what kind of resistor we have in each branch is going to determine the current for that branch. Okay, and that will follow Ohm's law as well. So within any given branch, the higher the resistance is, the lower the current is going to be through that specific branch. Okay. Okay, so moving on to, I just lost my spot. There we are. So resistance in parallel. When we're solving for resistance in a parallel circuit, this is a little bit different because we can't just add it together. And I'll explain why that is in a second. But basically what it boils down to is as you add resistors in a parallel circuit, your current of the overall system is actually going to increase, which can be a little bit confusing when you first think about it. But I have an analogy that'll hopefully help you out. So we can use this equation right here. 1 over R total, or equivalent resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. The way that I prefer to write it is to write it like this, where I have 1 all divided by 1 over R1 plus 1 over R2 plus 1 over R3. And then if you have, you could keep doing this. If you have 1,000 different branches, you could keep on doing that. Okay, but that is all equal to your equivalent resistance. That's the way I like to write it. If you do it this way up here, you're essentially doing the same thing. I just think you save a step by writing it out like this. But however you want to do it, that's fine. So this would solve for the total resistance or the equivalent resistance of an entire parallel circuit. So basically, if I were to take this entire thing and treat it as one giant resistor, that equivalent resistance you solve for is what it would be. All right, moving on to voltage and parallel circuits. So with voltage is actually a little bit easier in a parallel circuit because the voltage going to each branch in a circuit is going to be the exact same. All right, so if we have, like if we say this is a 12-volt battery, every single branch within this circuit is going to get 12 volts. So there will be 12 volts going here. There will be 12 volts going here. And there will be 12 volts going here. Okay, so in a parallel circuit, every single branch is getting the same amount of voltage. Okay. All right, now current in a parallel circuit. Now we have Kirchhoff's current law, and this one is where we are saying all current of the entering a branch must exit. So basically what we're saying is the total current in the circuit is the total current of all the branches. All right. So once you figure out the current in every individual branch, that is going to be your total current of the entire system. So for instance, if I say that I have 2 amps of current running through this branch, maybe I have 3 amps of current running through this branch, and I have 4 amps of current running through this one. Well, the total current of the system, so if I wanted to say current total, or sometimes I might say current EQ or equivalent current, is equal to 2 plus 3 plus 4. So we would have a grand total of 9 amps of current in this particular situation. Okay. In a series circuit, so this is where I have a little analogy for you to think about. So when we're looking at a series circuit and you add resistors, all right, you keep adding light bulbs, you are going to reduce the current. So if I were to keep adding bulbs to a series circuit, all those bulbs are going to use less voltage and they're going to get dimmer. However, in a parallel circuit, additional resistors are going to increase the overall current, right? Because what we just said was if I have, that is not what I want to do. If I have a bunch of different branches of current, you know, where they're all 3 amps, 3 amps, 3 amps. If I keep adding those branches and I have a whole bunch, well, that total current is just going to keep increasing and increasing and increasing. And the way that I would like you to, or that I like to think about it anyway, is I like to think of it like lines at a grocery store, right? If I think about each branch as a line at the grocery store, right? So I'm going to just pretend for a second here that these are like checkouts at a grocery store, right? And you have this register is open, right? And if that's the only register open and these two are closed, well, then you only have one path for people to go to, or you only have one register for people to go to. So the current or the flow of people going through the register is going to be relatively low. Okay, well, now if you were to go ahead and you open up this aisle now, or you open up this register, now all of a sudden there's another path for people to go to, or another path for people to check out their groceries. You're going to increase the flow of people. Just like in electricity, you're going to increase the flow of current. And I could do it again. I open up another aisle or another checkout, and now there's even more current or flow of people. So just kind of a way I like to think about it. You can think about it like that if you want to. That's just kind of what helps me. Okay, moving on to work problem number 3 here. Figuring out these can be a little bit tedious just because we kind of have so many different ways to. We are working with 2 different types of circuits, and we can kind of get confused between the two. But just keep in mind that you are always using Ohm's law. So you're always going to be using V equals IR whenever you're solving for one of these. What you really have to keep separate is kind of some of your rules. So keeping straight that within a parallel circuit, the voltage is going to be the same in every branch. And that within a series circuit, your current is going to be the same in every branch. So keeping those rules separate is kind of the tricky part. But we're always going to be using V equals IR. Okay? So first one says, what is the current in each branch? If I have R1 is 4 ohms, R2 is 3 ohms, and I'm not writing ohms just because I know I'm going to run out of room here. R3 is 2 ohms, and the battery is 12 volts. Well, so what is the current in each branch is the first question that it's asking. Well, we can figure out current, remember, by taking I is equal to V divided by R. So I'm doing voltage divided by resistance for every single one of these. And remember, each branch is going to be getting 12 volts. So this one's getting 12 volts. This one's getting 12 volts. This branch is getting 12 volts. So I can just take 12 divided by each resistor. So the first one, 12 divided by 3. All right, so let's just do, we'll do R1. Oh, nope, sorry, I'm not solving for resistance. So we'll call this one current, branch 1. That one's going to be, we're doing 12 divided by 4 ohms. So I get 3 amps. I2, we're doing 12 divided by 3 ohms to get 4 amps. And then I3, we are taking 12 volts divided by 2 ohms to give us 6 amps. Okay, sorry, I know this is getting a little bit cluttered here. It's best I got though. Second question, what is the total resistance of the current? So remember to find total resistance of a current. All right, since we're on another question, I'll change colors here. Total resistance, we're going to use that 1 divided by 1 over R1, which is 4 ohms, plus 1 divided by 3, plus 1 divided by 2. And whatever you get for that, that is going to give us our total. So take a second to pause if you want to solve for that, because I do as well. All right, so hopefully you got 0.923 ohms. Okay, so that is your equivalent resistance. Okay, so that is the answer to this question right here. So equivalent resistance is 0.923 ohms. What is the total current in the circuit? Remember, to find total current, we are going to take the current in every single branch and just add them together. So we already solved for the current in every branch up here. So all we have to do is add them together. So we have 3 plus 4 plus 6 to give us 13 amps. And then finally, what is the voltage drop across each resistor? Well, guess what? Your life is pretty easy here. Oh, nope. I'm sorry. Wait 1 second. Sorry, I got a phone call there. So your life becomes pretty easy here for this one because it says, what is the voltage drop across each resistor? So in this case, your voltage drop is just simply going to be 12 volts because every single branch is getting 12 volts. So you can just write 12 volts. All right. The only way this would be different is if for some reason you maybe had 2 resistors in a given branch. All right. If you had 2 resistors in a given branch, then you would have to go ahead and you would actually have to solve for the voltage in each resistor by taking the current running through that branch and multiplying it by the specific resistance of that resistor. But if we were to do that here, what I would end up getting is just 12 volts, because let's say we take this third branch, for example, here, where I have a 2 ohm resistor and I have 6 amps of current. Well, 2 times 6 is going to give me, ding, 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 12 volts. Okay. So, the last thing we're going to talk about here, and I'll try to wrap up quickly because I know this is going on a little long, is power. All right. So power is something that we talked about when we were talking about mechanical power, and we said that mechanical power was work divided by time, all right, or the amount of work done per second. Okay. Well, when we were talking electricity, we have to take 2 of the things we talked about. We're going to take 2 of those into consideration. We're taking current and voltage, and we are going to, or a voltage difference, and we're multiplying those 2. So power is equal to current multiplied by voltage. Remember, current is in amps, voltage is in volts, all right, or potential energy difference. And then power, if you recall, if you had me last trimester, I always said energy is energy, and I always said power is power. So power is still going to be measured in watts. All right. So if you recall that from last trimester, watts, or just capital letter W. Okay. Your assignment for the evening, make sure you complete that exit ticket on Google. And then also, day 5 and 6 assignment. Remember, you're not submitting that assignment, but hopefully you'll be able to solve for the rest of that or finish the rest of that. And I should have the key posted as well. Okay, hopefully you all have a great day.